I want to go to the next presentation. PLX is talking about laser tracking, and ABB and Epson were very interested about this, so I want to go there. New York, one of my favorite states in the whole United States and in the world. I want to know what PLX can do for the rest of the community. The floor and the attention of everyone goes to these fantastic three letters, PLX. Malcolm, the floor is yours.
Hi, thank you. So sharing my screen. Hopefully you can also see that.
Crystal clear.
Welcome to Disruptive Laser Metrology and Robotics. My name is Malcolm Humphrey. I'm the new Program Director for Active Optics within PLX. Come on, there we go. So I just briefly wanted to run through who PLX are. Probably a few of you have not heard of us as yet. Bit about MOST technology, the recent acquisition of Reflex Imaging Limited, and the new Active Optics division within PLX. So PLX have been at the forefront of photonics since 1955. They produce high precision optical components using their proprietary manufacturing processes. The invention of the hollow retroreflector back in the 70s was really the path for us for working with top military and mission critical projects. So last year in December, as it happens, saw the acquisition of Reflex Imaging, and that has really allowed us to increase the capability of our products. So for those of you not familiar with our MOST technology, it's our most popular technology at the moment. And this is about integrating multiple optical elements into a single monolithic structure that enables high degrees of stability in harsh environments without any loss of accuracy. So, as I mentioned, in December last year, PLX acquired Reflex Imaging, who were my old startup company. This really started off with Reflex Imaging approaching PLX with regard to the MOST technology, and we wanted to use it for our upcoming LAMM metrology system. We very quickly found that there's a lot of synergies between the companies, and that resulted in the acquisition of Reflex Imaging in December. So this collaboration has already yielded some interesting new technologies, which we'll hopefully talk about in future meetings. Okay. So the new Active Optics division, this is all about active optical devices, mainly based on MEMS devices. So anywhere we need accurate beam steering, scanning, modulation, that's what we're all about. An example of this is the former Reflex Imaging product, the LAMM device. So this is a bit of an overview of it here. So we have a diode laser. We've got a circular laser profile. This is deflected onto a MEMS scanning mirror. This in turn deflects the laser and a linear scan pattern. So we have, you see the various paths going out there. When that goes out of the unit via this beam splitter, you hit a retroreflector, we get a pulse of light back to the photosensor down here. So the way this works in practice is you would have the LAMM unit, in this example, scanning a smart target. It's scanning it in a plane because it's a 1D device. Whenever the laser dot hits a retroreflector, we get a pulse of light back. We know the angle of the mirror at the time of the pulse, therefore we know the angle between the LAMM and the reflector. We know the geometry of the smart reflector in this case, and so therefore we can work out the range, lateral position, and even using these two inner reflectors we can work out the vertical position. Now we did some evaluations for this with the Advanced Manufacturing Research Centre here in the UK in Sheffield. We looked at two potential applications for this. The first was tracking the position of a robot end effector in real time using two LAMMs and a known geometry. This was scanning in a plane. And this has applications for where your workpiece is relatively planar. So an aircraft fuselage or wing, for example, so where you need this large volume metrology. Another application, we're actually mounting the LAMM on a robot end effector. and we're using the robot to actually scan the LAMM across a workpiece. In this case, it is a reconfigurable assembly jig. So the robot would place clamps on the assembly jig, pick up the LAMM, scan where all the clamps are in relation to itself, and it can then start working on whatever task it needs to do on the assembly jig or the workpiece. So as I mentioned before, we have an upcoming project called the OLAMM. So this is where we're taking the single dimension scan device, and we're now going to scan in a volume. So this is really following feedback from many of our users as to what they would want to see in the LAMM product going forward. So very brief comparison between the upcoming OLAMM technology, which stands for orthogonal Laser Metrology Module. I should have mentioned that earlier. Probably the headline figure there is the sample rate of this device. So we can sample anything up to 256 targets with a refresh rate of 500 Hertz on individual targets. And we think that feature alone is pretty unique in the market. All right, photogrammetry systems can do that with conventional cameras, but they're limited by the refresh rate. And more importantly, the latency in processing that image. And as you can see, the latency of our OLAMM system is going to be very, very low because we're processing data on the fly and sending it to the host system on the fly. So some of the features of this and benefits: accuracy is probably one of the big ones because we're using our novel technology and MEM scanning mirrors, which are very stable devices anyway. We're seeing very good accuracy for these devices, hardly any drift. We haven't been able to measure any. And the way we see this being used is really to be integrated into a robotic manufacturing cell as a permanent fixture, because these are going to be low enough cost that becomes economically feasible to do that. And that will really reduce downtime by allowing you to eliminate calibration cycles for your robot. So at the moment you might use a high-end laser tracker system to periodically calibrate your robot. Because our accuracy is approaching that of the high-end systems, you no longer need to do that. And of course you're not losing accuracy in between those calibration sessions, so your overall productivity yield goes up. So what we're looking for is really some partners for us for this OLAMM project, specifically robotic integrators, to help us take the OLAMM technology and turn it into an end product or a full system where, that includes all documentation, calibration tools, the systems, the integration into the robotic control systems. These are real-time devices, so we fully anticipate them being able to be used for real-time robot control. And there'll also be opportunities for developing kit parts such as calibration and verification tools. And finally, what we can offer anywhere where you need precision laser beam steering, scanning, manipulation using MEMS devices, that's our expertise. We can, anything that's real-time processing, we can really help you with that. So thank you for listening. Do we have any questions from the floor?
Thank you very much, Malcolm. You can't imagine how many people are texting me that they want to get in touch with you afterwards to talk about this OLAMM project. This is really, really great. I want to find many potential collaborations here, and we'll come to them afterwards. But for me, I really always want to see on both sides of the supply chain how to collaborate. But I'm gonna get this out of the blue. Simon from Jabil, when you heard this presentation, what kind of opportunities do you see to integrate this OLAMM system into robots?
That was really an interesting talk right here. Thank you, Malcolm, for that.
You're welcome.
To be frank, I need to further understand, since you already also highlighted that the system costs are extremely low, or that's at least what I understood. And that would be a question, is that the double-digit US dollar range, triple-digit? Can you, let's say, narrow this down a little further?
Sorry, the range of the device, did you?
The cost range. You mentioned that.
Oh, the cost range. Sorry, yeah.
It's let's say feasible to implement this in scale. Where are we approximately?
Absolutely. I mean, it's based on MEMS scanning mirror devices. These are commercial devices. They're pretty low cost. You know, for low volumes, we're talking, you know, probably the cost of a car, you know, a cheap car, as an example. Obviously, we'd need to, you know, go through the process fully to actually come up with an end cost, but we are aiming for a cost figure that is below photogrammetry systems, well below laser, you know, the high-end Leicas of this world, you know, fraction of the cost of those. We want this to be economically feasible to fit into your, you know, $80,000 robot without driving up the cost of the manufacturing cell. Of course, the higher the volume, the better the cost becomes, because we're, you know, we're looking at the efficiencies of mass production now.
Definitely. Thank you for that. That helps me put this into perspective. And I asked Jose to put us in contact after the meeting.
Malcolm, I really love this slide, and I think it summarizes clearly what the OLAM is. You are trying to scan in volume.
Yep.
You are trying to approach this is 30 microns accuracy at 5 meters.
That's it.
It is awesome. It is great. Could you maybe share with us like the challenge that you will have for me to find the right company to help you on this? There are many, but you could point out the challenge.
Yeah, I mean, it would be great to, you know, work with perhaps another company that is developing this kind of technology as a partnership. It would be, I mean, one of the criticisms we had when we were Reflex Imaging is we were selling a what was called a prototype product, if you like. So we didn't have the software to go with it, the integration into the robot control system, all of that, those things that is, you know, essential to creating a system that you can then go and sell to the, you know, the Boeings and Rolls-Royce of, you know, and Fords of these worlds.
We will find you companies for working on that. But first, there's a question in the chat. It's coming from ABB Robotics. Jan, thank you very much for being with us today. What's on your mind?
I was just thinking about the interface, because you mentioned you have higher bandwidth by far compared to other technologies, and how do you transfer it also, and how is communication to the robot control?
So we can basically implement any interface that the user wants. What we have done with the existing LAMM products is we're using 100 megabit Ethernet for that with Modbus protocol. And the latency then becomes how well your network is performing rather than the LAMM device itself. Internally, we can, you know, output data very quickly within the device. It becomes more about limitations of your network. But as I said, if you've got a CAN bus there, if you've got RS422 or RS485, you know, that we can absolutely interface to that.
I also have a comment question. I also want to give the floor to Philip from CSEM in Switzerland. Philip, thank you very much for joining here. Any comments, suggestions that you can give Malcolm from PLX? This is a clear room for cooperation, in my opinion.
Oh yeah, we collaborated over the last couple of years together with Leica laser tracker. So this is, of course, then the high-end, much more expensive system. So I think it's very interesting from Malcolm that they go on a high accuracy and rather low cost system. We developed then the full control pipeline, and this is of course a lot of work. So we integrated the Linux real-time system where we achieved the data from Leica over EtherCAT with 1 kilohertz. And then you have to do a lot of processing, because it makes no sense to give 1 kilohertz to the robot control. So you have to do the right filtering, you have to move then the anti-swing movements, you have to compensate. So, yeah. But I think it's really interesting. So I posted the link to the Kraken project. So this is large scale. It's 22 meters by 6 meters. Okay. And accuracy is then, we achieve accuracy in the range of 300 micrometers, not 30, so 300, 0.3 millimeters.
Yeah, that's achievable. I mean, yeah, I mean, we're aiming for a range of up to 40 meters for a single OLAM unit. We're achieving 20 meters without any optimization today with the existing LAMM unit. The accuracy is angular accuracy, so it scales. So 300 microns at what, 30 meters, you said? That's probably within the range, the capability.
Malcolm, Philip, this is really a great room for cooperation. I'm a huge fan of the Kraken project funded by the European Commission, really an amazing European project. So I would like for you to have a look at that website. And thank you for a great presentation, Malcolm.
Thank you.
Christopher from Carter Robotics. So it was so great to have you at the meeting. We heard about so many technologies. I want to finish with a positive message, with something to make us dream. What is going to happen with the world of robots?
Well, if those of us have anything to do with it, it's to have the people not be afraid of what robots can do for humanity, and that there's so much that people can learn about themselves by just reflecting their emotions, their behavior, their dreams, their fears onto that machine, so that it can be communicated in a way that perhaps you hadn't thought of it before.
Christopher, I agree with you from the beginning of your presentation. You are too good to be true. Thank you so much for being in this meeting. And I would like to say that over the last 2 hours, we really talk about 3 key challenges. We talk about the control, accuracy, and speed. I borrowed this from Ian, from Epson. And on the control, the integration of RGB light sources, the integration of different passive and active imaging solutions working under low light and laser beam tracking. In accuracy, 3D shape preservation and sensor fusion are really the tool. And speed. Fast scanning with the laser was one of them, and actually incorporating on machine learning based hardware to have all these ideas that we have on machine learning really already in the robots. It was really great meeting. All I have to say is that I really can't believe that over 2 hours we talk about so many different topics and we scouted so many cooperations. Francesca keeps saying, we only have 5 speakers, 6 minutes each. Are we going to fill 2 hours? And Francesca said, of course we're going to fill 2 hours. We could have filled 20 hours. The only pity is that we cannot go for dinner now. Most important, the meeting is not over. If you want to get in touch with any of the participants today, jose.pozo@epictaxasoc.com and I will make those introductions. Please always remember that it is all about the follow-up. It's all about the follow-up. Don't just close your laptop and go for dinner now. Make sure that you follow up with the right companies and you find rooms for cooperation. Working together is the secret of EPIC. On behalf of an amazing team of technology experts in the medical, in integrated photonics, in the laser, in the optics, the best innovation manager in the world, Antonio Raspa, an amazing team of marketing and event management experts, and our CEO, Carlos Lee, the heart of EPIC, I would like to say thank you for making my dream of photonics in robots become true. This is the agenda of the upcoming online technology meetings for EPIC. If you see any interesting topic, like the one that we have on Meeting Friday on Wednesday, or on Monday on CMOS imaging applications, register online as soon as possible. Don't tell me didn't warn you. Until the next time, take care of each other, wash your hands and wear a mask. Be EPIC. Bye-bye.